We're all familiar with satellite imagery. We see it on our mobile phones. It powers the maps for ride-sharing applications. We use it to find trailheads. Most of that satellite imagery that you see today comes from Maxar, and we operate 4 high-resolution satellites to provide that. We had several goals for our next-generation satellite constellation. First, continue to support our existing customers, which drove the quality of the imagery that we provide. We wanted to increase capacity in high-demand areas, and that drove both the constellation size and mid-inclination orbits. And we wanted to enable high revisit use cases for monitoring. Most of all, we had to do this affordably. Now, we considered a variety of alternatives. For example, pairing a few large satellites with many smaller satellites where the small satellites provide revisit. But ultimately, we rejected that approach, and I'll explain why. We needed to maintain high performance in several key areas. For example, high resolution, necessary for you to identify what you're looking at and what it's actually doing. We needed positional accuracy, which is essential for applications like self-driving vehicles, where 1 meter accuracy is necessary to localize the position of a car within a lane on the road. We also needed sufficient capacity, because while it might be wonderful to find the unicorn of a single image that could fund an entire constellation, that's unrealistic. In the real world, you need to collect lots of imagery to be able to generate a return. Because, after all, the world is a really big place, and there are many interesting parts of the world that can be monetized. We have a metric for that, which is the number of gigapixels per day that we collect, and we use gigapixels per day because that allows us to normalize between 30 and 50 centimeter resolution, where 30 centimeter resolution is generally monetizable at a higher price. It's also important for us to be able to simultaneously image and downlink. When we're passing over a ground station, being able to image and downlink at the same time means that we don't waste any time maneuvering between imaging and downlinking. Instead, we can maximize our capacity while we're in range of a ground station. We also needed to optimize capacity versus demand because the world is not uniformly interesting. The most frequent change occurs where most people live. As you can see in this map, the population density is highly correlated with the rate of change. The world's population is also concentrated. Only about 8% of the land is considered populated. Half the world's population lives on less than 1% of the land. 95% of the population lives south of 50 degrees latitude. And we found that about 5% of the land drives 95% of the revenue. Metro areas are also large, and that drives a requirement for synopticity, in this case the ability to collect hundreds to thousands of square kilometers in a single pass, like this example of collecting the I-80 corridor between San Francisco and Tracy, California. Or even more importantly, for defense applications, being able to do force disposition analysis over an entire area simultaneously. Why is simultaneous important? Well, if you're taking a bunch of small pictures, it's like playing a game of Battleship, where your opponent can move the battleship between every move. Very hard to win that game. More like playing a game of whack-a-mole. Now, I mentioned mid-inclination orbits, and those allow us to improve our high-demand capacity. Remember, 95% of the world's population lives south of 50 degrees latitude. So we can double, or in some cases even triple, the number of minutes of access per month using mid-inclination orbits relative to sun-sync orbits. Mid-inclination orbits, however, do come with a downside, which is that the satellite is looking at a variety of sun angles throughout the day. So to avoid those blackouts, you need multiple satellites. So as one satellite is moving, say, into darkness, you have other satellites that are moving into the light. And we chose 4 mid-inclination satellites for Legion because that gave us a widest range of choices of sun angle for imaging a given location. It's also important to have good signal to noise because that allows us to collect imagery at those low sun angles, even with good resolution. Now, I mentioned mid-inclination orbits providing capacity, but they also provide intraday revisit. And depending on the resolution that you are imaging at, you can get up to 16 revisits a day from dawn to dusk with the Legion constellation. Now, those revisits are going to happen at a range of off-nadir angles. And why is high off nadir sometimes important? Well, looking at something at nadir, it's often difficult to identify what it is, unless you have an off nadir shot where it's immediately evident what you're looking at. In this case, it's my son when he was quite a bit younger. Now, that's not just true with happy snaps. It's important for defense applications as well. In the image on the left, you can see that there are hangars, but you can't see whether they're occupied. The high off nadir image allows you to determine that the hangars, some are occupied and some are not. Now, moving on to the system itself. How do you choose the size of the aperture? Bigger apertures are great. You can fly at a higher altitude to get the same resolution. That gives you a greater access area, better revisit. You need less agility on the satellite bus, but it's more expensive. And like in most engineering situations, it's a trade-off. So small aperture, the access area dominates, you need lots of satellites. Big aperture, your sensor cost dominates. And there's a sweet spot, the optimum for a given technology, which allowed us to select an aperture for Legions that's a bit less than 1 meter across. What about the focal plane? We looked at several approaches. The classic Pushbroom that drags the sensor along the ground. A framer, a 2D image that looks at the ground, staring long enough to get good signal to noise. A push frame, which is a hybrid, that is multiple framing cameras that are taken with successive images along the ground and then adding frames to get good signal to noise. Or a framer with a fast steering mirror, where the fast steering mirror both tracks the ground within an exposure and then moves rapidly to an adjacent area. Now, each of those approaches has pros and cons. They're qualitatively different. Pushbroom tends to be more expensive, but more capable. The others tend to be less expensive, but less capable. Let's look at some numbers. In area collection, Pushbroom is by far the most efficient area collector. In this case, looking at the rate of collecting at 50 centimeter resolution. It's also very cost effective. We can compare here a Pushbroom system, Legion, and a push frame system, the SkySat. If you look at the number of satellites to collect 1 million square kilometers a day at a normalized 50 centimeter GSD, it takes 75 SkySats to do what one Legion can do. When you factor in the satellite lifetimes and the amortized unit cost, non-recurring plus recurring divided by number of units, you find that Legions are at least 7.5 times more cost effective at collecting area than the SkySats. Legion's also more affordable than its predecessor. Worldview 4, which was started in 2009, 2,500 kilograms, $850 million for a single satellite. Legion started in 2017, $600 million for 6 satellites, 750 kilograms, triple the capacity of Worldview 4. Much more cost effective. How do we get that affordability? We do a block build to allow us to amortize the non-recurring over multiple units. Highly integrated electronics that reduces size, weight, and power and simplifies integration and test. Advances in optics manufacturing that allow both a faster schedule and lower cost. Cheaper launches. And efficient commercial practices that let us achieve high reliability. We give authority to empowered, experienced engineers, rigorous optimized testing across the constellation as opposed to every satellite being done the same, rapid decision making. The first block of 6 Legions is under construction for launch next year, and you can see photos of hardware bus build on the left, several photos of various tests that we do, and a photo of the telescope under construction, all 6. Now, I've talked about remote sensing as a business. But in addition to being a business, it allows us to also make the world a better place. Whether it's delivering the evidence for the Rohingya refugees, disrupting human trafficking networks, in this case, actually allowing 9 minors to be released from slavery, or aiding in an investigation a few years ago that freed 2,000 slaves from slave fishing and allowed them to be reunited with their families. And that's how remote sensing as a business enables us to also make the world a better place. Thank you.